Okay, so we want to write some of the entities like the momentum and moment of a momentum and kinetic energy and the power of a whole body in terms of its center of mass. So that's what we want to achieve. We'll just write that. We will show that the momentum in the F frame is equal to mvc by F. The moment of momentum in the F frame about point A is this, and the kinetic energy Tm, the power these are equations 2.29, 2.30, 2.31 and 2.32. Okay. So if you clearly notice, this and this is a contribution of two sums. Okay, is a sum of two contributions. The first one is as if the body were hypothetical, so these three, so 2.30 to 2.32 is a sum of two contributions. Now please focus on the first term of each of these equations. The first one is as if the body were a hypothetical mass point of mass m and moving with c, and the second term is due to the motion relative to c. Okay, so just for the sake of simplicity in writing, we will not be writing with respect to frame F. Okay, it will be ignored. So if you have this RPC, let me first draw this. Yes. Okay, so these equations which you see, you should see in terms of this figure I am drawing. This is clearly frame F, this is point O. Now this C is the center of mass. It has its velocity with respect to the F frame. Okay, there is a point O, A, sorry, okay, about which the moment of momentum has been written. This has a velocity A with respect to frame F. Okay, and now this consider a distributed mass. This is a small mass dm. This has a center point P. Okay, and this has the velocity of P in the F frame. Okay, now again you can consider this point I. It has, say, the force Fi and the velocity I with respect to F frame. Okay, so you can have point number 1, point number 2 and so on with own Vi, which V1F and F1, and for 2 it will be V2 with respect to F frame and F2 and so on. Okay, so this is Rp, this is Ra, okay, this is RCA, and this will be RPC. Okay, now so this is how you have to see equation 2.29 to 2.32. okay, I think all of the things are drawn. Okay, now if you want to write this summation over RPC into dm, okay, this would be 0. So let's see how do we say that. So this word quantity is equal to Rp minus Rc into dm. Okay, now this would be Rp dm m minus Rc into dm over the whole mass. Now this minus this will be 0. Okay, because essentially both of them are doing the same thing. Okay, so this Rc actually you can take out. So this would make this as Rp m minus Rc m. This is equal to 0. Okay, and using this, sorry, this would be, this quantity is Rc of m. Okay, this is equal to 0. Okay, now similarly you can say that Vpc dm is equal to 0. Okay, one easy way is to just say take a time derivative of this particular quantity. Okay, and then you should be able to get this, or you can just break down this individually, meaning you can write it as m Vp dm minus Vc dm. Okay, and proceed. So this is This is something which you should do on your own. So if you I'll write it, verify all here. Okay, now let's try to write the moment of momentum about A. So HA would have its contribution RPA into VP to dm. So RPA is a vector over here. Sorry. RPA cross VPA integral. So basically this is all the momentum of this small part dm is actually equal to VPA dm, obviously about point A, and that's how we are able to write this. Now this RPA you can break down into RPC, okay, and RCA. So you have to break them down as to RPA and RCA. So this vector is RCA, okay. RCA plus RPC is equal to RPA. So this you would write it as RPC plus RCA cross. Similarly, VPA also you can break them down into VPC plus VCA with respect to dm, okay, or m. Now you can take each of these terms. So RPC cross VPC dm plus RCA cross VPC into dm plus RPC cross VCA dm plus RCA, RCA cross VCA to dm, okay. This whole is integrated over m. Let me just write them separately. Integral, integral, integral. Okay. This is RPC. Okay. Now this is finally written as equal to H of C, H about C plus RCA cross MVCA. Okay. How do we do that? Let's see. So VPC dm integral, this quantity is 0, so this integral will move in. Okay. Similarly, RPC dm, okay, if this moves in, this is also equal to 0, and this particular quantity is actually equal to hc. So this is the moment of momentum about point C, okay, and hence HA is proven to be equal to HC plus RCA into MVCA, okay. So this is equation 2.30. Now let's see how the kinetic energy is written in terms of the center of mass. So the kinetic energy is equal to half into m into Vp square dm, okay. This this should be written like this, okay. There's no such thing as a square of a vector. Now this Vp square can be written as Vp dot Vp okay, and into dm. Now velocity of p can be written in terms of velocity of pc and velocity of c, just like we had done that over here. Okay, so this can be written as half into vpc plus vc, okay, dot vpc plus vc to dm. This would make it vpc whole square plus, so dm should always be there, plus then half goes to the next one, vc square dm. Okay, then you will have two terms, okay, half of vpc dot vc and half of vc dot vp. So I am writing them combinedly as vpc dot vc dm, okay, without the half because there are already two halves, and the rule is that a dot b is equal to b dot a. This is the property which we have used to write this. This can be written as half into m vc square plus half into m vpc whole square dm plus 0. Okay, so this quantity can be written like this. This quantity is over here, and for some reason this is equal to 0. Okay, the reason for that is if this dm is brought in over here, then vpc, and you can do that because dm is a scalar quantity. Okay, this is here, and this particular thing is equal to 0 because vc you can take out of the integral, so that's why this is 0. So you have now shown the proof of 2.31. Let's now take the expression for power, that is equal to I times fi dot vi, okay, for all the particles, and this can be written as fi dot vi is the velocity of this ith point over here, this one. Okay, this is vi in terms of f, and you can write this vi in terms of vc. So vi is equal to vic plus vc. vc plus vic. Okay, so this is something which we'll be using over there. So please draw the diagrams on your own in a notebook. Okay, you should not just be looking at the screen right now. You should be drawing the diagrams and doing all the derivations with a pen and a paper. Okay, now this quantity we can take the dot product separately. fi dot vc plus fi dot vic dot vc. Okay, now this quantity can be written as f dot vc plus f dot vic. So this has been written because this summation will not act over VC. Okay, over here you cannot do it because I is there in the subscript. So that's why this continues to be written as sigma fi dot vic. So that proves the expression 2.32 for power. So the defined entities of momentum, I think, was already shown before. The moment of momentum and the kinetic energy and the power in terms of the center of mass has been derived, as we had written in the green color. So if you now have so you have the frame F and this is, say, the point 1. It has this force F1. It has point 2. It has force F2. Velocity of the center of mass is c. Okay, and say the nth point is Fn, having a force Fn. Okay, now the rate of work done by external forces on a rigid body, okay, which is shown in this figure, is W dot is equal to clearly Fi Vi over all the discrete points. Now if there is a rotation of this body, okay, with the omega obviously with respect to F, okay, so this the velocity of the ith point then can be written as the velocity of the center of mass plus omega cross RIC. Okay, so omega is the angular speed of angular velocity of rotation of this body. Now this can be written as Fi dot Vc and the I, okay, plus you can have sigma I into Fi dot omega cross RIC. Now this sigma Fi can be written as F because Vc is independent of that, and then this quantity can be written as omega dot RIC cross Fi. Okay, and there's this summation over I. Now how is this equal to this? Well, that can be written in this form. This is, I think, called the scalar triple product, and you should verify this. Okay, so sigma Fi is taken over there, and I think the trick with the sigma or any integral term is just to see any term after it, if it is independent of the I, like for example Vc over here or omega over here, you can just take it out like we have done over here. Okay. So this is equation 2.33. Sorry, this is not equation 2.33. We have to simplify this further. So W dot is equal to F dot Vc. F is the total force, a total external force, plus mc dot omega. Okay, and this whole quantity is mc, the moment of the moment about this point C, and this is because A dot B is equal to B dot A. So this is 2.33. So this implies that the work to equivalent, now looks okay, I shouldn't do this, I should actually put this in, I should put this in green. So this implies that W dot is equal to F dot Vc plus okay, and I want to now say this. Okay, I'm drawing an equivalent force system, same thing. Now the forces are looking like this. There is a center of mass. Okay, there is this point Q. There is this couple acting over here. Okay, and then there is an omega. This is frame F. Okay, so if you have the total force F and then you have an mc of the center of about the center of mass C, then you can just write this quantity. So both this and this are equivalent force systems, and hence you can say the work done will be the same. So you can replace this complicated force system over here by something which is much simpler, which is having just force and the moment. Okay, so this implies that two equivalent force systems perform the same work on a rigid body. How do we say that perform the same work? Well, you can just take an integral of this from time t1 to t2 and then you would get the total work done. Okay. So this quantity, I mean, we have not separately. So if you were to say replace this by an equivalent force system which has just a force F and then you had an MC, okay, you would just get this quantity. Now if you had this couple moment acting, you know that the work done over here would be MC in this green figure would be omega. Okay, there's no F and that would be C dot omega. Okay, so let me put that out in words. Okay, let me just okay, so this is omega. The work done by the distributed uniform gravitational force on a rigid body is the same as that due to its resultant. Okay, so sigma fi has been replaced with f. Of a rigid body is so this is from equation 2.33. Okay, so I'm sorry for telling you that this is an equivalent force system. This was just actually much more simplified case, this green one. Okay, an equivalent force system would be that if all these complicated forces over here is just replaced by one force at the acting at the center of mass and the moments about the center of mass. Okay, so this is the equivalent force system for this one, and that's what you get in equation 2.33. Let me put that just to amend my correction. Let me do that over here. Okay, so there you have it. Okay, so we now want to find out the relationship between the time rate of change of moment of momentum about a point A and the moment about point A due to the forces. Okay, so that's the relationship which we are trying to find out. So let me just give out the answer like the previous section beforehand. Okay, so Euler's second axiom takes the form MA minus RCA cross MA, okay, for an arbitrary point A. Okay, now let me just show that first with a diagram. Okay, and then let's have this rigid body like always. Let's have the F frame, no sorry, I frame. Since we are talking about Euler's frame, Euler's axioms, we have to work in the I frame because Euler's axioms are only valid in this frame, the inertial frame. So let's call this RC, the center of mass. Arbitrary point is A. Let's call this RA. Okay, this automatically becomes RCA. Okay, and the acceleration of this point can be, okay, I should have a vector acceleration of A with respect to I. Now this has a MO, okay, and this has an F. Okay, so let's see how this works out. So using equation 2.30, let's see what it was. 2.30 is HA, okay, HA is equal to HC plus RCA cross, okay, this is a cross, why should I, okay, cross MVCA. Okay, Now clearly f will not be there, we will be only talking in the terms of the I frame. So all the f's will get by I over here. So I'll write that once again. Using 2.30 we can say that the HA in terms of the I frame is HC in terms of the I frame plus RCA cross MVC A by I frame. Okay, and since it can be written for A, it can also be written for O. Okay, so HO minus I HC. Since A is an arbitrary point, well, why not O then? Okay, similarly it will be RCO cross MVCO this implies that HC in terms of I is equal to HO. Okay, and this will be a minus sign, minus RC. I'm not writing O over here since it's very clear what it means. Similarly VC with respect to the I frame. Okay, now I can write H. So what I'll do is now I will substitute this over here. Okay, so I'll write HAI is equal to HO with respect to I minus RC cross MVC I plus RCA cross MVCA in the I frame. Okay, this is good progress. Now we will take a time derivative of this. Okay, time derivative of the above equation. Let's see how do we do. So H dot is equal to HO dot. Now there are two terms. I'll have to apply the chain rule. So VC of I cross MVC of I minus RC cross M AC with respect to I. So this term is now done. I now move to the next term, that is VCA I cross MVC A plus RCA cross MACA. Okay. Okay, so this is the second term, this two terms. Okay, let me just now remove this. Okay, now we want to write this as MO minus RC cross F plus RCA cross M A of CI minus A of A by I. Okay. Okay. this quantity will clearly be 0. Okay, so since VC cross VC will be 0. Okay, and then you have RCA into MCA cross, let's see, RCA, yes, okay. Now this quantity gets cancelled with over here, fine, and C cross F. So this particular quantity, okay, is written as this, okay, and this particular quantity is written as this. So ACA is equal to AC minus AA. So that's there, and MO will clearly be now using the Euler's second axiom as this quantity. Okay, so this quantity is again equal to 0. Okay, now MO, I'll just rub all this, okay, so that it's easy to write. It anyways goes into the recording, so you can always pause or rewind. Plus RCA cross MAC minus RCA cross MA times of I. This is MO minus RA cross F, okay, and this would be minus RCA cross MAA with respect to the I frame, okay, and this implies that H dot AI is equal to MA minus RCA cross MAA in terms of I. Okay, so this quantity is MA, and this quantity okay, so this can be okay, this, so let me use different colors over here. This is the same as this, okay, and this should be equal to RC cross MAC minus RA into MACI, okay, so this quantity will cancel with this quantity and you will be left out with this, which is written over here, okay. So this is what we have. This can be written as equation 2.35, and it's already given, but H dot O in the I frame is equal to MO M into acceleration of the center of mass by I is equal to F, and MO minus RA cross F is equal to MA, okay. Okay, now looking at 2.35, H dot A will be equal to MA if, okay, so for arbitrary point A, this H A dot is not as simple as this O, which is the part of an inertial frame. Okay, so the only way this will be true, H A dot will be equal to MA, uh, that will only happen if one of the following holds. What's the first one? AA is equal to 0, that is A has 0 acceleration in I. The second possibility is that AA is parallel to RCA. Okay, in that case this particular cross product will be 0. Acceleration of A is along AC. So you can look up this figure. The acceleration of A has to be along AC. In that case also this will hold true. Or the third case is that the RCA is equal to 0. Okay, that clearly means the arbitrary point is the center of mass, that is A coincides with C. So this will give you a very useful form, which is H dot C is equal to MC. Okay, this is 2.37. so if you are using the H dot M relationship at the center of mass, you can just simply write it like this, and this is very useful. That's why you see that for many problems when you use these relationships you will be trying to get hang hold of the center of mass. Okay, now if you look at 2.36, if MA is equal to 0 in equation 2.36, then okay, now one of the other statements which must be made over here is that equation, since both of them are visible right now, equation 2.36 and 2.37 is derived using F is equal to MAC and H dot O is equal to MO, and so is not independent. And the proof of it is, I mean, you see we have already used this okay, to derive 2.36 and 2.37, so it's not independent of these. This implies that you cannot treat them as a new information for your system. So once F is equal to MAC of I and a moment equation have been written, then writing another moment equation will not yield an independent equation. Okay, so please don't think that you will first write 2.36 and then you will write 2.37 and that you will give some get some new information. You won't. It's essentially the same equation coming from the same F equal to ma and the moment equation. So this is not a new information as such. So please don't ever do that mistake. Okay, first write it about arbitrary point, and so they are not independent. I mean, it may be convenient to write it in one form or the other, but they are not supplying any independent information to your problem. And you will see that when you try to solve problems regarding this. Okay. So if you have, say, equivalent mass system, something like this, so you have this point C, okay, and you have this Fr, which is the resultant of all the forces, and then this is a CRC equal to MC. So you can write everything in terms of the center of mass. Now let's take up a few situations. We are considering a motion of a uniform disk rolling without slip. Okay, so for example, if you have this moves V naught, A naught, this is point E, this is point D. Okay, there's clearly no slip, and this is point C, this is R, you have this as B, acceleration of B, okay, A is acceleration of A is equal to 0, and this rotates by omega and omega dot. Okay, so you can consider three cases over here. One is that V naught is equal to 0 and A naught is equal to 0. The second is that V naught is not equal to 0 and A naught is equal to 0. And the third is that V naught is not equal to 0 and A naught is not equal to 0. Okay, let me now take an elevator. So now the uniform disk is rolling without slip. Earlier it was rolling without slip on a conveyor. Now it is rolling without slip on an elevator. Okay, so I'll do this again. E D no slip Okay, this point is h. Okay, it should have been an h over here as well. Now since it's an elevator, this will be going V1 up and A1. Okay, so we have situation 4 over here such that V1 is not equal to 0 and A1 is equal to 0, and situation 5, V1 is not equal to 0 and A1 is not equal to 0. And then one can have the rolling of a disk without slip on a step of an escalator. Okay, so in this case we'll have point T, H, C, B, A, B, A, acceleration of A is 0, R, again no slip. This time this should have a V2, A2. So the two possibilities over here as V2 is not equal to 0 but A2 is equal to 0, and 7 V2 is not equal to 0 and A2 is not equal to 0. So if we write 2.36, okay, 2.36 is about A. So out of all these equations, you should actually verify this. I'll write it in this. So equation 2.36, which is HA dot I is equal to MA, is valid for points A, B, C for all 7 cases. Okay, verify this. See, you already know when 2.36 will be valid. It will be valid when either the acceleration of A is equal to 0 or the acceleration of A is parallel to RCA or RCA is equal to 0. Okay, so you have to please check the point A, B, C in all these 7 cases and know that which of these 3 conditions is satisfied. Okay, that's the first part. And after this, for the other cases in which it is not valid, you should be sure that neither of those 3 requirements is valid. So, okay, so this is the 3 conditions which you must check. So check for other points, which is what D, E and H. Why not for D, E and H? So for D it will be case 1, 2, 4, 5, 6. For E this will be valid for 1, 2, 4, 6. Okay, and H it will be case 5. So you have to verify all of them. it should be very easy for you to do this. Okay. So let's now sort of discuss this H. We haven't really dealt with this HC dot MA relation, okay, where HC dot is the time derivative of the moment of momentum about the center of mass, and MA is the moment due to the forces about an arbitrary point A. Okay, so relation for arbitrary point A. So we want to have an equation which looks like this. Okay, 2.3, where did it go? 2.35. okay, we want something like this. Obviously this time over here we are looking for C, okay, and the rest of it should be same. So what we'll be doing is we will be utilizing this fact that the resultant of external forces will be this. Okay, this is the resultant of external forces, and now we want to write everything in terms of this. So please have a good look at this equivalent force system. So this is the resultant. Okay, so CRC is the couple, so that is shown as equal to MC. Now FR, let's just write that, FR is equal to F is equal to MAC of I CRC equal to MC equal to H dot C. Okay, this is something which we have already shown above. Okay, that's why this equality we are able to write it like this. The system consisting of a force MAC of I and a moment H dot C of I acting at C is called the kinetic system. Now the moments MA and MAB of the external force system are the same as moments of its equivalent kinetic system at C. So if you want to write MA, that will be MC plus RCA cross FR. Okay, this would be H dot CI plus RCA cross MAC of I. Okay, this implies that MAB is equal to H dot CI RCA cross MAC I dot E. So this is quite useful in problem solving. Okay. So now you have this relationship between H dot C and MA. Okay, this has come up because you knew MA is equal to MC plus RC across FR. Okay, now this is something which you can do. Try to tell where this equality is coming from. Okay, this will be a good exercise. So you have to go back and figure out where this equality is coming from. This part is okay. Okay, we have just done this, but try to see if you can figure this part out. Okay. Now we want to finally write HA. So these are all special cases of what we have just seen. H dot HA dot is an MA relation for any point A for a translating frame T. Okay, for this you remember we have done discussions about a translating frame T earlier, so many of those properties we'll be using over here. So this is a good time to just pause and go back and check what were the properties which we have already discussed. Okay, so over here let's consider a frame T which is translating relative to inertial frame I at okay, so the velocity and acceleration are given like this, and body B of mass m in motion relative to t. Okay, so if we have to write this, let's in a diagram. So you have an inertial frame I, you have a translating frame T. Okay, clearly you have this point O, it has Vt, it has Vt and At. Then this is the body B in frame M. Okay, take a point over here, a small sort of mass like this. Consider an arbitrary point over here. This is the center of mass C. Okay, now this particular point may have a velocity of A with respect to t. it may have an acceleration with respect to t. T is the translating frame. This has a velocity of a with respect to the inertial frame I. It has an acceleration of a with respect to the inertial frame I. This is RCA. This is this is RPA. Okay, velocity of P and then velocity of P in the T frame. Okay. Okay, so now we want to say that the velocity of point P, the continuum point P in the I frame, can be written as the velocity of P in the T frame minus velocity of T. Okay, I hope this is okay. And similarly, and we have done all this. Okay, it's not that the first time you should be seeing all this. If you do not recall, you can always go back and check from where this is coming from. And the most important part is that for any time derivative in the I frame is the same as any time derivative in the T frame. Okay, so recall, where have you seen this? Okay, you have to go back and check this to the translating frame discussion and verify that part written is correct. Now this would imply that the velocity of PA in the I frame is the same as velocity of PA in the T frame, just because the velocity of PA can be written as RPA dot. Okay, so using this we are saying this. Now if you have for body B F is equal to MAC of I equal to MAC of T plus MA of T. Okay, so what we have done is we have just written this acceleration of center of mass in the I frame as the summation or the relative acceleration of C in the T frame plus the acceleration of T. Okay, it is needless to say that this T is actually in terms of the I frame, but we are not saying that explicitly anywhere. That's why I am not writing. Okay, this implies that MAC with respect to T is equal to F dash. Okay, and clearly where F dash is equal to F minus or so plus minus MAT. Okay, so this is the sum of forces of an augmented force system consisting of external loads on body augmented by and inertia force MAT minus MAT acting at C. So let's see how does it look like. So let me do that over here. So if you have, say, at the center of mass you have mg acting, okay, and at point 1 you have F1 acting, okay. So this minus of 80, you see how we can do that over here. So let's just say this is G, this is minus of 80, okay, acceleration of T, okay. Since let me see, acceleration of A is where in my figure, it's like this, okay. So minus of 80 would be minus of 80, okay. Okay, and we can say that this is a G equivalent, okay. So the resultant of this G and minus of 80, okay. Now we can say that it's the same body, okay, even if the diagram doesn't look like that. So this is the C couple, moment due to a couple. You will have at C, you will have an mg, and you will have a minus of mat. One remains as it is, 2 remains as it is, okay. So this can be seen as something like this, okay, with at C, rather than writing now mg and mat, we can write a mg equivalent, okay, and everything remains the same. Okay, so this is the augmented force system. Okay, so this equivalent dash, whatever you would want to say, will have this F plus of minus MAT. Okay, now let MA dash is equal to MA plus RCA cross minus MAT, okay, be the moment of the augmented force system about A. Okay. Now you can note that MC dash is equal to MC, since this RCC will be equal to 0. Okay. So you can write for body B HA in the inertial frame is equal to MRPA. This is just the definition of momentum. VPA I dm. Okay, that tiny mass over here, this is dm. Now this is RPA dot VPA in the T frame because of this. Okay, and hence this means that this is HA in the T frame. Now let's write HA in the T frame is clearly equal to HA in the I frame. We have just shown this. Okay, this and this will be equal to HCI plus RCA cross MVCA I. Okay, now how am I writing this? I think we should have written it somewhere. Over here. Okay, using 2.30. So let me put that over here. .30. Okay, now this is equal to HC in the I frame plus RCA cross MVCA in the T frame. Okay, just because this in the I frame is the same as in the T frame because of the reason which we have just discussed over here. Okay, this one. Please recall where and how we have derived this. Okay, otherwise it will keep on spiraling into a big problem. Pause the video and go back if you do not recall why this is happening. Okay, now we will take a time derivative of this, and that will make this as h dot a T frame is equal to h dot c in the I frame plus RCA cross M into ACA in the T frame. Okay, it will also have another term. Okay, VCA cross M VCA of T. Okay, this will also be T, but the problem is this cross this will be 0, so that's why we are not writing that. So it will just be these two terms. This clearly will be equal to MC because this quantity is equal to the forces of the moment due to forces about the center of mass. We have shown that earlier, plus RCA cross m, acceleration of c in the t frame minus acceleration of a in the t frame. Okay, so now this we want to write in terms of the augmented systems. So m dash c is plus RCA cross f dash minus m a by t. Okay, now clearly in the translating frame we have been writing it as MAC in the translating frame has been written as f dash. We have already said that somewhere. Okay, okay, this would be equal to, take this term and you would have m dash a minus RCA cross MAA in the t frame. This implies that H t is equal to so in the translating frame this HA dot will be equal to MA dash if point A is coincident with C, or okay, if coincident with C, then this RCA will be equal to 0, or acceleration of A within the t frame is 0, okay, or the acceleration of A t is along AC, it is parallel to RCA. Okay, either of these cases this can be written. So if you look at equation 1, where did 1 go? Okay, equation 1, okay, and equation 2. So by 1 and 2 we can conclude that the force momentum relation, that was 1, and moment of momentum relation 2 relative to t have the same form as those relative to I. Obviously the difference is the augmented force system with the augmented force system replacing the external force system. Okay. So here, for example, when you would say this was the external force system. Okay. And if you replace this by the augmented force system, you can still write the force moment and moment of momentum equation about the point A if there is a translating frame T. Only thing is you have to replace it by a augmented force system, which is over here. Okay. Okay. So, and you remember we have defined a kinetic system somewhere. I think I don't remember where we have defined. Perhaps, yes, a system consisting of a force mac and a moment uh, c dot acting at c is called the kinetic system. So for this augmented system, the kinetic system will simply be, again it's the same body though that looks weird, but so it should just have mac in the t frame and h dot c in the t frame. This is the kinetic system for the same force system. So force system is this. Okay, let's call this as the external force system. You then have the augmented force system, and then this is the kinetic system, all representing the same forces, external forces on the body. Okay, so let's now move to our next topic, which is called equations of equilibrium. Okay, so let's have lots of figures over here. I draw this body like this of a weird shape so that you don't get an idea that it should be like a perfect cube or a cuboid and something like that. Okay, it can be of any shape. So this body has this part P1, part P1, P2, Pi, it has a mass Mi, it has Pn. Okay. Let's see. I will keep on drawing this. Okay, so if this is the body which you have, okay, it has a total mass m, body B, total mass m. Obviously you are seeing all this from the I frame, and clearly it indicates that the Euler's axioms are in play. So a system is said to be in equilibrium if every material point P belonging to it remains at rest in an inertial frame. In an inertial frame. I. Okay. If a system B is in equilibrium, then for the external load system on every part Pi, okay, you will have f of Pi is equal to 0 and Ma for this Pi is equal to 0, equation 2.40. We'll prove this now, okay? We'll prove this. So if a system B is in equilibrium, then for the external load system on every part Pi, this is true. A system is said to be in equilibrium if every material point P belonging to it remains at rest in an inertial frame. So let's start with that. Every point P belonging to it remains at rest in an inertial frame. That means that the velocity of P with respect to I is equal to 0. Okay. Now what I draw over here is this Pi, okay, this is Pi overall, and this is of a mass Mi. Point on this is P, this has a mass dm, okay, this has a velocity of P 0, okay, F1, F2, okay, and I mean all the boundaries of this okay, all the boundaries of this have this moment and forces, moment and forces, moment and forces, because it's in touch with, say, parts P1, P2 and whatever this is, let's call it P3. Okay, so all of these faces of this part will experience external forces, and this I frame sits here nicely. O, there is this arbitrary point A, so this is the force, external forces on Pi, this is the external moment on Pi about point O. Okay, so let's call this dm. Okay, so we have written that the velocity of P in the I frame is 0. So for a point O in this I frame, velocity of PO will also be 0. Okay, so that would mean that the velocity of PO in the I frame will also be equal to 0 for all time t. Now for part Pi, the momentum, okay, this is the Euler's axiom we are using. This would be equal to mi and then v of p I dm this would be equal to 0 because all the Vp in the I frame is equal to 0, and this is for all time. Similarly, HO in the I frame is Mi, and okay, this is integrated over this part of small part Pi, which is having a mass Mi. So that's why the integrations are over Mi. This will have RPO in I cross VPO I Tm. This would also be equal to 0 for all t. Okay, so just because VPO in the I frame is equal to 0 because of this. So the Euler's axioms yields if Pi is equal to P dot I is equal to 0. Okay, so the rate of change of momentum of this is equal to force, and the rate of change of momentum is equal to the moment. So this will be MO. It will be for Pi is equal to H dot O in the I frame. This is equal to 0. Okay. The others are, let's say, if you want to write now the moment of this part Pi about an arbitrary point A, it will be by this relation which we have used many times until now, plus AO cross FPI. Okay, so this is an arbitrary point A, and you want to write the moment about this point of this part Pi. Okay, so this is the relation. Again, please recall where and how we had derived it. Let no doubt creep in your mind. This is somehow equal to 0. Why? Because this quantity is equal to 0 and this quantity is equal to 0, f of Pi. So that makes it equal to 0. And over here, A could be any point of the system or outside maybe in arbitrary motion. So this should be called 2.40. Okay, so you can apply or extend this 2.40 to all the parts of this. Okay, and then you can write that equation 2.40 holds for the complete system be in equilibrium. So f of B is equal to 0, MA of B is equal to 0. Okay. Since it's valid for each point, each parts individually, it will be valid for the whole body as well. Okay. So there are some important points which we must note at this place. So first of all, let's call this equation 2.41. Okay. Equations 2.41 are necessary conditions for equilibrium. Let me just write equilibrium like this, but not sufficient. Even for a single rigid body. I'll explain this now. So you have a uniform, an example of this, a uniform rigid cylinder. Okay, circular cylinder rolls without a slip with the uniform angular velocity on a horizontal plane. Even though the external forces on this body is 0, okay, and the moments about an arbitrary point is equal to 0, say the point of contact. So these conditions are satisfied, but still the body is not in equilibrium. And why do I say the body or the cylinder is not in equilibrium? Because every material point P belonging to it does not remain at rest in the inertial frame. Okay, that's how we had defined a system is said to be in equilibrium if every material point belonging to it remains at rest in an inertial frame I. So this is important for you to note. Now equation 2.40, let me just put that 2.40, f of pi is equal to 0 and ma of pi is equal to 0 are also equations of motion of an idealized inertialess so in other words, it's very light, mass is negligible system. Since m is equal to 0, this implies for all parts pi the momentum in the I frame is 0 and the moment of momentum about O is also equal to 0 for all t. And when do we say something is light? Okay, when can we idealize it as light? When the force of gravity is very small compared to other forces acting on it. Very small compared to other forces acting on it. Okay, in that way you can just take mg is equal to 0. So essentially when the accelerations are small and small with respect to other things, I mean when you say that the length of this body is small compared to the other dimensions, okay, so something is small or large with respect only to the other. Okay, so in cases where the accelerations are very large, for example if there is an impact analysis, say the crash of a car or something like that, then the accelerations are quite high. In that case you can't make these idealizations. Okay, so before we close this topic of equations of equilibrium, we have one tiny but extremely important concept to learn. It's called a two-force member. So a two-force member is a member subjected to only two external forces and no couple. Okay, so if a two force member is is in equilibrium, or a two force inertialess, okay, if it's a massless, we have seen that the equations are the same whether it's in equilibrium or it's massless, we have seen just above, is in motion two forces have equal magnitudes opposite directions and act along the line joining their points of application. I'll show it with a diagram. Let's show that as a proof. So if you have, say, okay, let me draw this over here. If it is light or in equilibrium and you have this F2 F1. This is the line joining. Similarly, if you have, so it's the same body, okay, again and again I'm saying this. This is F2 minus F1, and clearly this is F1, line joining like this, or F2 is equal to minus F1. Okay. So these are actually very similar cases. So if two force member is in equilibrium or two force inertialess member is in motion, then the two forces have equal magnitudes, okay, opposite directions, and act along the line joining their parts. So let's consider this first part now, okay. It's all either light or in equilibrium. So let's try to prove this. MA about any arbitrary point is this, but since we want to cancel the contribution due to one of them, we'll take it about this point A, will be equal to AB vector cross F2. This is equal to 0, okay, and this is there because there is no moment, okay, there is no, it's a two force member, is a member subjected to only two external forces and no couple. This would imply that F2 acts through along AB, okay. Similarly, if you can do it, say MP, that would be equal to BA cross F1. This would be equal to 0, and this would imply that F1 acts along AB or BA, okay, same thing. Since the summation of external forces is F1 plus F2 is equal to 0. It can be 0 because of two reasons. One is that it is in equilibrium, and secondly it is light, okay, it's inertialess. So either of these two cases this can hold true, and this implies that F2 is equal to minus of F1. So there are two possibilities this can happen. One is either this or one is either this. So a two force member can only exist in either this form or this form, okay. So that's the reasoning that two force member has to exist either like this or like, so we started off assuming that it is something like this, but we found out that the only possibility is this or this, okay.